Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome to 6th lecture of VLSI Interconnects course. Today we will be discussing about equivalent circuits for RC interconnects. In the previous lecture we saw Elmore delay for RC tree networks and RC branched interconnects. We saw that how in the limit n tending to infinity, that is the number of elements tending to infinity, we get a nice elegant closed form expression for our Elmore delay. However, if we want to simulate an interconnect accurately in a SPICE simulator or any simulator, we will be required to break down that interconnects into large number of resistance and capacitances. However, what happens is that having these large number of sections just for interconnects is computationally expensive, and therefore we require an equivalent circuit to take care of the interconnect. So this will form the topic of our today's lecture. Let's get started. So in the last lecture we saw something like this. So if I have a branched interconnect something like this, I would be and I want to incorporate that, represent that with an RC circuit, I would require a structure like this, where there would be large number of these R into delta x and C into delta x, and throughout for all these segments. However, so for this we get an Elmore delay, there is no issue. However, if you recall our discussion in lecture, number 1, we saw that finally we need to take care of these interconnects in more complex circuits like this. So there is a circuit where there are large number of components, the devices that needs to be taken care into the simulation. But now just for these branched interconnects you require these type of distributed elements. So if you want to simulate this interconnect in a circuit simulator, or suppose we just want to simulate that interconnect alone, there is a problem. We don't want very large number of interconnects. We cannot afford that each of these line segment is broken down into 10 resistors and 10 capacitors. That will increase the number of components in our circuit exponentially. So what we want is, we also want an equivalent circuit model, so equivalent interconnect model. The point the constraint is that it should give me the same Elmore delay. So if I have an equivalent circuit and I want to, from that circuit equivalent circuit, if I want to get the Elmore delay, for which I can now write a simple code if I know the connections between resistors and capacitors, I want an equivalent circuit to fulfill that need. So let us see how we can do that. So your equivalent circuit should satisfy the following two requirements. First is that your number of elements should be small. Of course, there is a trade-off between the number of elements and the accuracy, and we will investigate this in more detail when we take up the simulation of interconnects. So, but overall we can't afford to have, say, 10 or 20 segment RC components just for one connecting wire. In previous courses you are just connecting it by a shorted wire, right? So think about like all the wires that are there in your circuit, and now if you want to replace each of them with 10 resistors and 10 capacitors, it becomes a problem. So we want the number of elements to be small. However, we also want the equivalent circuit to give the same expression. If I draw an equivalent circuit of my interconnect, or of my total circuit replacing my interconnect with its equivalent circuit, the delay which I get should be the same as that for the distributed model. So this is the constraint. Otherwise, I could have just replaced my interconnect by a lumped R and C but then it will not give me the same Elmore delay if I do an analysis of this entire circuit. So what we will do is the following. So let us first consider, because now this has to deal with, say, the driving circuit and the final load device also. So let us consider the source resistance and load capacitance in our Elmore delay. So you have an interconnect like this. This is your input device and this is your output. This is your output device. Length of your interconnect is L, the resistance per unit length is R and capacitance per unit length is C. Now this input device is having some resistance. I am writing this as RD because in literature this is called as, say, the driver resistance. This is your driver device. So this is the driver resistance. And then your output device, for output device we are considering some capacitance. So this is replaced by your capacitance. So this is your load capacitance. So if we now if I now want to consider the Elmore delay with this source and load, how should I do? Now what is your input? Your input is here Vi and your output is this. So this is your Vi. So now your transfer function, what you are interested in is V out of S by V in of S. But now, I mean, now since we are familiar with how to compute Elmore delay, we are not required to compute this transfer function, this and this, considering RD and CL and all. What we know is that there is a resistor and we follow the same approach. So my path now is starts from here, my path starts from here to, and it goes till from here till this point. In my path, what I have, let us take the resistors and the capacitors and follow the same procedure which we did for getting the Elmore delay. So if I want to get my Elmore delay, what will be my first resistor? My first resistor will be R into D, and sorry, RD. RD would be multiplied by all the subsequent capacitances. So what are the subsequent capacitances? The net capacitance of your interconnect is so your C interconnect is C into L. So you will have C into L, and then you will have this load capacitance. So you will have plus C subscript L. So this is just RD. This is the delay which is introduced by just RD. Now let us take the second segment. In this segment, what do I have? This interconnect delay would be there, this interconnect delay, this would be anyways be there. So what we know? We know that this interconnect delay is RCL square by 2. How do we get it? Basically we again take the infinitesimal segments and multiply the resistors. So from this point to this point, just as we solved in the previous lecture on branched interconnects, we will be getting a term of R into L in R into C into L square divided by 2. But now for each of these small infinitesimal resistors, this capacitance CL is also loaded. So what we will have is, we will have a sort of summation over these resistors and each of that will be multiplied by CL also in addition to this term. So, we will have another term of this resistors R into L, this resistance into CL. So, this will be your load, so this will be your total delay. So, if you want to get what is the total delay along your interconnect, considering the source and the load terms also, in that case your total delay is given by this. Now, what we want to do, we want to replace this connection. There is a device here and then there is this other device. This interconnect is now adding some additional delay. We want to incorporate that in our circuit simulation. We don't want to have infinite number of segments here. So, what we will do, we will replace this by an equivalent circuit. Recall what was the condition? The equivalent circuit should give the same Elmore delay as the distributed model. This is the delay for the distributed model. So, let us try to think about an equivalent circuit which will give me this model. So, one of the approach is this using a pi equivalent model. There is another approach of T equivalent model that we will not be specifically discussing, because that is very similar to what we are doing here. So, I have this interconnect and this has terms of CL and RC L square by 2 and then RL here. We need this in our term. This is our circuit. So, let us take the pi equivalent model. In pi equivalent model, what we do is that we simply replace the resistance, simply replace this interconnect by a single resistance, by a single resistance like this. The resistance is R into L. This is basically you are considering a lumped resistance for the interconnect. But I am not, we will not be making a complete C into L here, because if we do that, there would be a problem that your Elmore delay will not be matching. So, remember, for this interconnect your delay was R into L into C into L divided by 2. So, what was happening is that your capacitance was distributed throughout the length, and then that you can sort of average out by writing like this. So, you will have C into L by 2 and C into L by 2. Now, if you try to write the Elmore delay for this, you will be getting terms like R d into whatever is the total capacitance. So, C into L by 2 plus C into L by 2. So, you will have C into L, I can directly write C into L plus the load capacitance C L plus then you will have R into L into C into L by 2 plus R into L into C L. So, this would be matching with your expression here, right. You can check that. So, this is a pi equivalent model. Here what we were doing is that we were replacing this inductance the interconnect by a single resistance R into L. We can have a more accurate model also. So, this is replacing your interconnect by three terms. We can suppose we can afford more number of terms in our circuit. What we can do is that we can break this interconnect into two segments like this, each having a resistance of R into L by 2 and R into L by 2. So, basically what we are doing is we are breaking this into 2. So, in that case I will be having a circuit like this. Right. Now, what about the capacitances? So, this capacitance would be, this is broken down in, right. So, your length is now reduced by 2. So, this will be your this will be your C into L by 2, right, and then this again there will be something here, and this will also be C into L by 2. This segment will also have C L by, sorry, this will be C L by 4, not 2. So, this is dividing into 4, this will be C L by 4 and then C L by 4. Now, if you club this all together, what you can do is that you can replace this this entire thing by a single capacitor. So, if I do that, I can simply replace this entire thing by a single capacitor, and that will give me a single capacitor of C L by 2. Here this is R L by 2 and this is also R L by 2. For this you can also check your Elmore delay. So, if you write your Elmore delay, again your R D will be multiplied by all of this. So, this will be C L by 4 plus C L by 4, which is C L by 2, that added to C L by 2 is C L plus C L like this, plus if I take the second term. So, this will be R into L by 2 into all the subsequent capacitors. So, C into L by 2 plus C into L by 4 plus C L plus C L plus so, this is this term, then R into L by 2 into C L by 4 into C L by 4 plus C L, and then and plus this into C L. So, if you solve this all, you will be still be getting the same expression. This can be further extended. So, if you want to have more terms, more number of terms, you can also have a pi 3 equivalent model. So, when we take the lecture on simulation of RC interconnects, we will be considering these pi and pi 2 models and comparing it the accuracy of your simulation with a distributed and a lumped crude model, right. So, now let us take this example. So, what we now have is an interconnect, branched interconnect like this. We want to draw the pi equivalent circuit model of this following layout, and you want to also find the Elmore delay. So, what we will be doing is we will be taking each of these segments one by one and then replacing it. So, there is this one segment. So, here we are taking only the pi equivalent, right. So, we are not taking pi 2 or pi 3, we are just taking pi equivalent model. So, each of this segment would be replaced by one resistor, right. So, this would be replaced by this resistor. So, this is length L. So, this would be R into L, right, and then this is R1 and C. So, this will be R1 into L, and this is R2. So, this is R1 into L1, this is R2 into L2, right, and similarly for capacitances. So, here the capacitance is C for all of these, to keep it simple. So, this will be C into L by 2, this will be C into L by 2. This will be C into L1 by 2, this will be C into L1 by 2, this will be R into L, this will also be R into L, because I have given the lengths to be equal to keep the number of variables less. Then this will be C into L by 2, this will also be C into L by 2 to L by 2 to L by 2. So, if you want to look at the terms, so basically this segment is replaced by this segment, then this segment is replaced by this segment of your circuit, this replaces this, then this part is represented by this part, and say this part is represented by this part, right. So, this is how you are doing. Then you can then club these values of capacitors also. So, here you can club all these three capacitances. So, you will have C into L here plus C L 1 by 2. So, here the capacitor will be C L plus C L 1 by 2, this will be R L, right. So, this will be R L, this will be R 1 L 1, R 2 L 2, C L by 2. What will be this capacitance? C L by 2 plus C L by 2 plus C into L 2 by 2, C into L 2 by 2. So, if I combine all of this, C into L plus C into L 2 by 2, and here the final term will be the same as this C L by 2 by 2. So, this is the equivalent circuit of your branched interconnect. So, this is your the equivalent circuit. From this, now if you want to find the delay, Elmore delay, it is lot more easier. So, T say 1 to 3. So, suppose I want to find T 1 to 3. There are only 2 resistors in my path now. So, those resistors would be, so yeah. So, those resistors would be, so T 13 is, this does not contribute unless I am having a source resistance. So, if there is source resistance, some R D, that would be also contributing. Right now, this will not be playing any role. So, you have R into L, and then that multiplied by all the summation of all the subsequent capacitances. So, what you have is this. So, you have CL plus CL plus CL by 2. So, you basically have 5 CL by 2 plus CL by 2 plus CL by 2, sorry, CL 1 by 2 plus CL 1 by 2, and similarly here C L 2 by 2. So, you add this here. So, basically you will have C into L 1 plus C into L 2. Way of looking at it is this, that this resistor, this first resistor is charging this entire capacitance plus this entire capacitance plus half of the capacitance of that segment, and also these both these capacitors. So, this is just the first term from point 1 to point 2. Now, from point 2 to point 3, if you want to go, you will have to add another term, and which is this. So, this is simply R 1 C into L 1 square by 2. Similarly, if you want to find the delay between 1 to 5, in that case what you will be doing is you will be the first term will be there. So, you have to go from 1 to 5. 1 to 5 is this path. So, if you want to take that path, first term is there, first term remains the same, second these terms will also be there. So, let us write them down. So, you will be having R into L into 5 CL by 2 plus CL1 plus CL2. This is the first point from 1 to 2, then you go from 2 to 4. So, in 2 to 4 you have a resistor of R into L, that is charging how many capacitors? The capacitance of this segment, which is equal to C L by 2, plus half the capacitance from this segment. So, basically you are charging 3 C L by 2 here. So, you have 3 C L by 2, and then the capacitance of this segment, so which is C L 2 by 2, sorry, into C L 2, the complete interconnect. And so, this from here you have come from 0.2 to 0.4. Now, from 0.4 to 0.5 is simple once unbranched segment. So, you have R L 2 into, or I can directly write R into, yeah. So, this was R 2, right. So, this will be R 2 into C into L 2 square divided by 2. So, this will be your delay from 0.1 to 0.5, right. So, this will be your Elmore delay, right. So, I will end this lecture by again giving you a problem. So, a circuit is given to you, there are different elements to your circuit. So, there you have a branch interconnect like this, all these have different materials and different thicknesses. So, this is the aluminum segment. For the element segment, the thickness is 5 micrometers and the length of this segment is 1 mm. This is sort of a global, I mean the long distance interconnect which is there. Then from there you go closer to your devices, where there is a section here of interconnect formed by polysilicon with silicide, and then there is this these segments which is formed by polysilicon. So, all these are symmetric. So, this is 10 micrometers. So, this is also 10 micrometers. This is 200 micrometers. This is also 200 micrometers. Width here is 0.5 micrometer and width here is 0.25 micrometer. For this, what you have to do is you have to draw the equivalent circuit of this interconnect tree shown below. Take these values and get the values of R and C of those elements of the equivalent circuit, and then you have to compute the Elmore delay. So, for this some information is given to you. Sheet resistance for these three materials is given to you. Sheet resistance is basically this resistance in this form, which we had discussed in lecture 1. So, reference lecture 1. If you do not recall, basically your interconnect resistance is related to your sheet resistance. This is sheet resistance R with subscript drawn like this in the form of a square here. So, this is equal to length divided into width divided by width. So, your width is this. So, suppose you want to get the resistance for this segment. So, if you want to get say resistance of R aluminum segment, what you will be doing is you will be multiplying R this into this length here, and divided by this width here. So, that will give you the resistance of this interconnect. Similarly, you have to do for other interconnects also, and for each of these segments, aluminum, polysilicon with silicide and polysilicon, it is given to you what is the capacitance per unit length. So, getting the capacitance is, or say of that interconnect is simply C into L, and these lengths are also given to you. So, for that you have to draw a structure like this for that, and here it is given to you that this A auto farad per micrometer. So, auto is 10 to power minus 18. So, with that you have to compute the equivalent circuit. So, I will just give you how the equivalent circuit would look like. So, there would be one term like this, and then there will be capacitance. So, this will be for aluminum, then there will be branching like this, and then there will be further branching. This is symmetric, right. So, this would be so this will be polysilicon, and this will be your polysilicon, and this part will be polysilicon with silicide. So, you have to get these values. There would be some capacitance also. So, either you draw it there, or you can club all these capacitances also. There will be one capacitance here, net capacitance, and then there will be one capacitance here and one capacitance here. You can also draw here, but then you can combine all of these together here also. So, get the values, and then you can solve it to get the Elmore delay for this, say from 0.1 to 0.5, or this is symmetric. So, any point you can take, right. So, yeah. So, in today's lecture we saw the equivalent circuit of interconnect. We saw that we can represent an interconnect with pi equivalent models. With small number of elements you can represent your interconnect, and this basically also helps you in getting the expression for Elmore delay in distributed model, and if there is a complicated RC tree, making an equivalent circuit makes it easier to estimate the Elmore delay, right. So, in the next lecture we will be looking at the effects of scaling on the interconnect delay. How the scaling down of dimensions is affecting the devices and the interconnects, and why interconnects are becoming the bottleneck in designing your VLSI circuits. That is all for today. We will meet in the next lecture. Good day.